So this video goes over chapter 13.2, which is finding limits algebraically. So in the past section, we found the limit using a table of values. But in this video, we're going to learn how to set up a way to find those algebraically without having to do a table of values. And this way is more soundproof than doing the table. Okay, so suppose that c is a constant and the following limits exist. So we have the limit as x approaches a of f of x and the limit as x approaches a of g of x. And we're going to go ahead and define our limit laws. So we have that the limit of a sum, so we have the limit as x approaches a of f of x plus g of x equals the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So basically, the limit of the sum is the sum of the limits. And then we have the limit as x approaches a of f of x minus g of x equals the limit as x approaches a of f of x minus the limit as x approaches a of g of x. So our limit of a difference. So the limit of the difference is the difference of the limits. And then the limit of a constant multiple. So if we're multiplying c times f of x on the inside of the limit, we could take that c out and do c times the limit as x approaches a of f of x. And then we also have the limit of the product. So when we have f of x times g of x in the inside, we could split those up into the limit as x approaches a of f of x times the limit as x approaches a of g of x. So the limit of the product is the product of the limits. And then our limit of a quotient, we have the limit as x approaches a of f of x over g of x equals the limit of x approaches a of f of x over the limit of g of x. And this holds if the limit of x approaches a of g of x is non-zero. So the limit of the quotient is the quotient of the limits. And then we have, I just did the limit of the identity function. I think I go over it later, but I just wanted to go over it here too. So if we have for f of x equals x, the limit as x approaches a of f of x, that's just equal to the limit of x as x approaches a because f of x equals x. And this equals a. So some more limit laws, we have the limit of a power and the limit of a root. So if we have the limit as x approaches a of f of x to some power, then this is just the limit as x approaches a of f of x and then to that power. So that would be like if we had the limit x approaches a x plus 3 cubed. That would be like if our f of x is x plus 3, so we could do the limit as x approaches a, x plus 3, and then cube that. And then the limit of the root is the same thing as the power, but our root is just a fractional power, basically. So the limit of x approaches a of f of x to some n root equals the n root of limit of f of x. So if n is even, we're assuming that the limit of x approaches a of f of x is greater than 0. Okay, so we're going to use limit laws and the graph of f and g in this figure to find the different limits. So have the limit as x approaches negative 2 of f of x plus 5 times g of x. So from the graph, I could see the limit as x approaches 2 of f of x is 1. So we have our f is the red. So let me go ahead and do the red. So I have 1 and this is 2. So our limit there is this point, so it's 1. And the limit as x approaches negative 2 of g of x is, I change to blue, is here. Then it's negative 1. Okay, so let's go ahead and split our limit up. So I'm going to go ahead and do the sum So I'm going to split them up. So I have limit of x approaches negative 2 of f of x plus the limit as x approaches negative 2 of 5 of g of x. And then I could do my constant multiple rule, and I take out the 5 from in here and I place it on the outside. So now I could just plug in the values that I found from the graphs. So I'm going to have 1 plus 5 times negative 1 is negative 4. Okay, and then for the limit as x approaches 1 of f of x and g of x. So let's look at our graph. So the limit as x approaches 1 for f of x, that's this value here. So that's 2. And then the limit as x approaches 1 of g of x, let's see. So for g of x, I have a jump discontinuity. And so basically the limit of g of x as I approach from the right is negative 1, but then as I approach from the left, it's negative 2. So these limits don't match. So the limit of x approaches 1 of g of x does not exist because my left and right side limits don't agree. So therefore I can't do the product rule, so this limit does not exist. And then I have the limit as x approaches 2 of f of x over g of x. So the limit as x approaches 2 of f of x, that is here. So it's approximately 1.4. And then the limit as x approaches 2 of g of x, that is 0. Because it's my y value at 2, and that's 0. So the limit of g of x as x approaches 2 is 0. So I can't do this quotient rule. It does not exist because the denominator is 0. So I can't do that. And then our last limit, I have the limit as x approaches 1 of f of x cubed. So we, from this problem, I found that the limit of x approaches 1 of f of x equals 2. And then I'm basically just going to move the cubed to the outside to the whole thing, doing my power property. And so I have the limit as x approaches 1 of f of x is 2. So 2 cubed equals 8. Okay, so now I have some special limits. So basically I have, this is like the constant. So c is just some real number. So the limit as x approaches a of just the constant function is going to be that constant because it stays the same. Then I have the limit as x approaches a of x, that equals a. So that's like the identity that I went over earlier. I have the limit as x approaches a of x of n equals a of n. And then the limit as x approaches a of the n root of x equals n root of a, where n is a positive integer and a is greater than 0. Okay, so let's do some examples. So I have the limit as x approaches 5 of 2x squared minus 3x plus 4. And I could go ahead and split these up using sums and differences. So I have the limit of x approaches 5 of 2x squared minus the limit as x approaches 5 of 3x plus the limit as x approaches 5 of 4. So I could take out the 2 for the constant multiple, get 2, limit of x approaches 5, x squared minus, and I could take out the 3, limit x as x approaches 5, and then the 4 just stays the same. So now, using this limit law, I could just go ahead and plug in the 5. So I have 2 times 5 squared, because that's my a, minus 3 times, and then this is the identity now. So I have minus 3 times 5 plus, and then this is a constant. So I could use my constant law, and then plus 4. So that equals 39. Okay, so now we have the limit as x approaches negative 2 of x cubed plus 2x squared minus 1 over 5 minus 3x. So I could use my quotient rule, so I split up the limits, and then I could do the sum rule. So I have the limit as x approaches negative 2 of x cubed plus, and then I could take out my 2 constant, plus 2 limit of x squared as x approaches negative 2 minus the limit of 1, and I just take out the negative 1 basically, or the negative as x approaches negative 2 of 1. And that's over the limit as x approaches negative 2 of 5 minus 3 times the limit of x approaches 2 of x, so splitting up using the difference and then taking out the constant multiple. So I have negative 2 cubed plus 2 times negative 2 squared. So I'm just plugging in the negative 2 basically for my x's. And then my constant is just negative 1 over 5, because 5 is a constant, minus 3 times negative 2. And that gives me negative 1 over 11. Okay, so now that we've done that, we're ready to talk about limits by direct substitution. So we've kind of seen already in these examples, I was just kind of plugging in negative 2 after doing the limit laws, but now we have this property where if f is a polynomial or a rational function and a is in the domain of f, then the limit as x approaches a of f of x just equals f of a. So basically we're just plugging in our limit or our a value into our function and solving. So for example, I have the limit as x approaches 3 of 2x cubed minus 10x minus 8. So now I could just go ahead and plug in the 3. So I have 3 cubed minus 10 times 3 minus 8, and that equals 16. So I could do that because my f of x is a polynomial. And then in this next example, my f of x is a rational function. So I could go ahead and plug in a. So my a is negative 1. So I could just do negative 1 squared plus 5 negative 1 over negative 1, 4 plus 2 is negative 4 over 3. So in these cases, I'm seeing the behavior as x approaches some a. And you could just do this by direct substitution. Okay, so as we've seen before, sometimes the limit, the x approaches a, sometimes f of a doesn't necessarily exist. So sometimes we have to work harder, like when the denominator is 0. So not necessarily that doesn't exist, but it would equal 0, and then the limit basically wouldn't exist. So in this case, we can't just directly substitute x equals 1 because f of 1 isn't defined. Because when we plug in 1, we have 1 minus 1 is 0 over 1 squared minus 1 is 0 over 0. So f of 1 is not defined here, and the limit of our denominator is 0. So we could factor and do some preliminary algebra in order to solve this limit. So I'm going to go ahead and I leave my x minus 1, but on the bottom I do my difference of squares. So I take the x squared minus 1 and I turn it into x minus 1 times x plus 1. And then I could cancel my x minus 1s. So I get the limit of 1 over x plus 1 is 1 over 1 plus 1, which is 1/2. And then for this next example, I have the limit as h approaches 0 of 3 plus h squared minus 9 over h. And so I could go ahead and I just expand this, basically because if I plug in 0, I get a 0 on the denominator, which is undefined. So let's see if we could do something. So I expand and I get 9 plus 6h plus h squared minus 9 over h. And then I could go ahead and subtract the 9s from each other. So I just get 6h plus h squared over h. And then I could actually factor out an h from the top, and I get 6 plus h over h. So then these h's cancel. So I'm left with limit as h approaches 0 of 6 plus h, and that equals 6. Let me fix that. 6. Okay. So in this next example, I'm going to go ahead and find the limit by rationalizing. And I could rationalize the numerator. So I have the limit as x approaches 0. So I can't use my quotient law because the denominator is 0. So I just go ahead and multiply the top and bottom by the square root of 4 plus x plus 2 over square root 4 plus x plus 2. So we did rationalizing fractions in previous chapters, so we go ahead and use that here. So when I multiply, I do square root 4 plus x times square root 4 plus x. And basically those cancel, the square roots cancel because it's the square root of 4 plus x squared. So that cancels, and I'm left with 4 plus x. And then I have plus 2 times 4 plus x, but then that cancels with the minus 2 times square root 4 plus x, so I don't write that. And then negative 2 times 2 is negative 4. So I have that. So I have 4 plus x minus 4 over x times square root 4 plus x plus 2. My 4's on the numerator cancel, so I have x over x times square root 4 plus x plus 2. The x's cancel, so I just have 1 over square root 4 plus x plus 2. So now I could go ahead and directly substitute, and I get 1 over square root 4 plus 2, which is 1/4. Okay, and so a way to tell if a limit exists, in the previous section we said if the right and left hand limits don't agree, then the limit doesn't exist. So let's go ahead and compare left and right hand limits to see if the limit exists in these cases. So I have showed that the limit of x approaches 0 of the absolute value of x equals 0. So recall that the absolute value of x equals x if x is greater than or equal to 0, and then it's equal to negative x if x is less than 0. So I'm going to go ahead and do the limit as x approaches 0 from the right-hand side, and then the limit as x approaches 0 from the left-hand side of the absolute value of x. So I have the limit as x approaches 0 from the positive side. That's going to be when my x values are greater than or equal to 0. So I could just plug this in for my f of x. So the limit as x approaches 0 from the right of x, I just plug in 0 and I get 0. And then I have the limit as x approaches 0 from the left. Those are going to be the values that are less than 0. So I could go ahead and plug in negative x for my f of x, because those are going to be my y values. And then I have the limit as x approaches 0 from the left of negative x equals 0. So our left and right hand limits match. So the limit as x approaches 0 of the absolute value of x is 0. So we're good for this one. We've shown it. Okay, so for our next example, I have proved the limit as x approaches 0 of the absolute value of x over x does not exist. So I'm going to go ahead and do the same thing like I did in the previous example. I'm going to take the limit as x approaches 0 from the right and the limit as x approaches 0 from the left. So for the right, I could plug in x for my absolute value. So the limit as x approaches 0 from the right is x over x, and that's just 1. So the limit as x approaches 0 from the right of 1 is 1 because this is a constant. So then from the left, I have the limit as x approaches 0 from the left of the absolute value of x over x. That equals the limit as x approaches 0 from the left, and I could plug in my negative x like I did here, and that's negative x over x. So the limit as x approaches 0 from the left is negative 1 here, and then that's just a constant, so it's negative 1. So I could see here that my left and right hand side limits are different. So therefore, that means that the limit as x approaches 0 of the absolute value of x over x does not exist. Okay, I'm going to go ahead and end the video there, and we'll continue the next video with chapter 13.3. So follow me there.